All right, hello. So, my name is Jernej. I'm an assistant professor at the University of Southern California in Los Angeles. Before that, I was a postdoc at MIT, and I got a PhD from Carnegie Mellon. And in case you are wondering, I am originally from Slovenia. So, my background is a little bit unusual because I've done my bachelor's degree in mathematics, but then I switched to computer science. And I do computer graphics, real-time physics. I apply the results to medicine, CAD/CAM, also interested in IP law, technology, and startups. So to give you a bit of a background of what I do, suppose you're given this kind of a model of a bridge. And now what you want to do is compute the dynamic deformations of this bridge under some given external forces. So you can apply the finite element method, and you can compute this motion. This is a solved problem in physics. The issue here is that the computation is very slow. So it takes 10 hours to compute these 5 seconds of the animation. What I've done is I made this a lot faster, actually about 100,000 times faster in this example. So now I can have an interactive system where I can pull on the bridge in real time and I can see the response immediately. Because now it only takes 0.1 second to compute 5 seconds of the animation. So the result is quite good. There's a downside. It's not as accurate as the slow solution, but it's quite plausible. So the way it works is you take a high-dimensional system, and then you find some low-dimensional basis of motion, and you project the equations of physics to that low-dimensional space, and then you can time-step in the low-dimensional space a lot faster. So one application is virtual medicine. If you're a surgeon, you may want to train some surgery. You can train now on a simulator, on a computer, rather than on a real patient. I think because my system is fast, you can simulate human tissue in real time inside the actual virtual surgery simulator, which hopefully will lead to fewer mistakes in medical training and in medical practice. Another application is contact. Suppose you have two very complex objects, both objects having very complex geometry and also deformable. What my system can do, it can resolve collision detection and contact between these two complex objects, and it can simulate the deformations of them at very rapid rates, like 1,000 times per second. This is super useful in robotics to keep the robotics mechanism stable. So one application of this is also virtual assembly. Suppose you're an engineer, you're designing the interior of an airplane, of an engine. You often want to check whether the mechanical components fit together, whether you can move certain parts in between very narrow clearances. And so you can use this kind of a system to prototype in virtual reality on a computer, which avoids the need to build an actual prototype. Right? So you can design the engine much faster. You make fewer mistakes, you design it faster, and hopefully it will lead to eventually safer airplanes, safer and cheaper airplanes, cars, spaceships, helicopters, basically any mechanical system. You can see the system is very robust. I'm pulling very hard here. All right, so when will this be on the market? For the deformations part, I'm talking to Weta Digital, which is a special effects company from New Zealand, Avatar, Lord of the Rings, many other films. For the contact part, I'm talking to a company in France for potential applications in the automobile industry. And here are some challenges that I'm facing. What I'm finding is that the industry usually wants it for free, right? Or else they don't want to deal with you, especially in computer graphics, because there are so many computing technologies is that if you're not willing to just give it for free, basically they don't really follow up. Often they're also quite secretive. They don't want to share the data sets. We don't want to give you the model, the texture, because we're afraid you're going to leak to the competition, and then our secrets of the next movie will be revealed, and so on. Right? I'm also like a lone assistant professor, just like 2 or 3 students, not a big company with 20 people. And another issue is that sometimes, university has its own idea about intellectual property, but industry has other ideas. So sometimes it's a bit of a conflict, and I have to do a lot of negotiations to manage this. All right, thanks for your attention. I'll be happy to talk more about this later.